Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. I spent a lot of time wading into the pencil and paper math associated with a simple reactive circuit, which consisted of a single resistor and a single capacitor. You can see this video. I've put a link to it up there in the corner just for you. Well, we can avoid all of that heavy lifting and save a lot of pencil lead if we leverage the capabilities of Excel to do it for us. And this is exactly what I will be covering in today's video. I've provided a link to the spreadsheet created in this video in the description. It also includes the results from the pencil and paper exercise from the previous video. If you have questions or comments, please feel free to add a comment to this video. I make a concerted effort to respond to every single comment. If you find this video helpful, please click on the like and don't forget to subscribe. So let's begin our video by getting Excel ready for the festivities. While Excel has the native capability to do what we need to do, it does not come with those capabilities enabled. Enabling these capabilities is a two-step process. The first step is to reveal the Developers tab. The Developer tab will also give you the capability to record macros and a bunch of other fun stuff like this right over here. Visual Basic, macros, record macros, all kinds of cool things. So look across your ribbon up here at the top and see if you can find a tab labeled Developer. If it's not there, then we need to reveal it for you. On any one of the tabs that you see here, right-click, click on Customize the Ribbon. The Excel Options box opens up. Customize Ribbon section opens up. And over here on the right-hand side, Customize the Ribbon, we come down. We find the Developer tab here. We make sure that this checkbox is checked, and then we click on OK. At this point, we should be able to see our Developer tab right here. Now we're ready to go on to the second step. First, we need to verify that we need to do this. So we click on the Formulas tab. We look in the function library over here to more functions under engineering, and we see all this stuff, all this IM. If this stuff does not exist, then we need to install the Analysis Toolpak add-in. To do this, we go to the Developer tab, we go here under Add-ins, and it says Excel Add-ins. We click on this. The add-ins dialog box opens. Add-ins available. We have Analysis Toolpak, so on and so forth. This is the one that we want right up here, this Analysis Toolpak. Make sure that this is checked and click on OK. Now, when we go over here to Formulas, More Functions, Engineering, we should be able to see all of the things that we need to do what we need to do. So, we are now ready to go into our project. Now we need to do a quick introduction to the new cool functions we've enabled in Excel. Here are the ones that we are immediately interested in. Complex. Complex is the first one. It creates a value in a cell of the spreadsheet that Excel will recognize as a complex number. It has three arguments: the real portion of the complex number, the imaginary portion of the complex number, and the suffix you want to see. Now that'll either be I or J. Now in electronics, we use J because current already has the market cornered on I. The second one is imaginary. It returns the imaginary portion of a complex number. It has a single argument, which is the complex number. Then we have IMREAL, which returns the real portion of a complex number. It has a single argument, which is the complex number. We have IMABS. Well, that doesn't seem to make any sense. These kind of made sense, but IMABS, well, it returns the magnitude of the complex vector defined by the single argument of the complex number. Then we have IMSUB. Well, that's the subtraction or the difference between two complex numbers. It has two arguments. The first is the complex number to be subtracted from. The second is the complex number which is being subtracted from the first. Then we have IMSUM. This one's a little bit different because it returns the sum of anywhere up to 255 complex numbers. It has two or more arguments, which are the complex numbers to be added. We have IMDIV, which is division. It returns the result of dividing two complex numbers. It has two arguments. The first is the numerator, or the top part. The second is the denominator, or the bottom part. And finally, we have IMPRODUCT. IMPRODUCT returns the result of multiplying up to 255 complex numbers. It has two or more arguments, which are the complex numbers to be multiplied. Now that we have this introduction under our belt, we can turn our attention to the circuit we're trying to analyze. So here we have our simple circuit. It is an AC voltage source connected across a series combination of a 10 k ohm resistor and a 1 nanofarad capacitor. The output is across the capacitor itself. That's it. Now we have the standard equation for voltage gain of a voltage divider. V out over Vn is equal to the output entity divided by the sum of the input and the output entities. In our case, Zn is the same as Rn, and its impedance Zn is going to be equal to Rn, the value of our resistor, plus 0 times J, because there is no reactive portion of it, so it just simply becomes Rn. The output entity is the capacitor here, so Z out is equal to the impedance of this capacitor, which is minus J divided by 2 times pi times F times C. But this entity right here, this 2 times pi times F, is the frequency in radians per second and is often represented by the lowercase Greek letter omega. So this becomes minus J over omega times our capacitance. So this is Z out. So far, this doesn't look too much different than what we were doing with the pencil and paper math. We're still in the same place. However, this is where we diverge from that path. Let's tell Excel how to do it for us. To make this make sense and be easy, we must be organized and thoughtful in how we set up our spreadsheet. Unfortunately, the complex math functions in Excel do not necessarily get along with named cells very well, so we're just going to have to remember what is what and lock things down on our own. The first step is to create cells for the component values. You can see that I've created a cell here for Rn. I put the value here in C2, labeled it in C1. I created a set of cells for the capacitor in D2 for the value, and I labeled it in D1. Over here, I put in the units so that I knew what units these values were in. We have a frequency-dependent design, so that means that we need a column filled with frequency values. So I chose to start my frequencies at A6, so I had room for all of my labels and stuff here at the top. And for this particular design, I chose to start at 1 hertz, proceeding at 1 hertz steps until I reached 100 hertz. Then the step is 100 hertz until I reach 10 kilohertz. Then the step is 1 kilohertz until I reached 100 kilohertz. And finally, in 100 kilohertz steps until I reached 1 megahertz. The equations use radians per second, which is represented by the symbol omega, and it's equal to 2 times pi times the frequency in hertz. So I'm going to create another column here in column B, which is our omega. To do this, I go to B6, and I enter the formula equals 2 times pi, parenthesis, parenthesis, times $A6. Now you may say, well, what is this $sign all about? Well, normally when you copy stuff from one cell to the next, Excel does a favor for us. It increments the address. The $sign prevents Excel from incrementing that address attribute when we copy it. If it resides before the letter or column attribute, then the column attribute will not change. If it is before the number or row attribute, then the row attribute will not change when the cell is copied. All right, so we have our equation in here, and we're going to copy it down the entire column by double-clicking on this little box in the lower right-hand corner. Bang, there we go. All right. Now, we have to remember that our equations all have impedances in them. They're dependent upon impedances. So I'm going to create a column for the impedance of each component in my design. In this case, I have my resistor and I have my capacitor up here. So I'm going to create a column Zn equals Zr, and so we're going to create a column of values which is just the impedance of the resistor. Now, in order for Excel to do its thing, this value here must be in complex form. Even though this is just a resistor, it's got to be in complex form. So to do that, we use the complex function. So equals complex $C$2. That locks this down so that when this cell is copied, it'll always point to only this cell. I can copy it to right, left, up and down. It'll still be just this cell. And this resides in the real portion. Because this is a simple resistor, there is no imaginary portion that goes to a 0. And then the suffix is J because we are doing electronics. And we have entered our equation. And so now we're going to copy that down the entire column by double-clicking. Now we come to the equation for the impedance of our capacitor. Impedance of the capacitor is equal to minus J over 2 pi FC, but 2 pi F is our omega, which resides in column B. And again, this has to be a complex entity. So we start out complex. This is a capacitor. There's no real portion, so that's 0. And then we have our equation for the impedance here, minus 1 divided by $B6. So that's this cell in this column. In this case, it will not increment moving left and right, but it will increment moving up and down, times $D, $2, which points to this cell and only this cell. So there's our equation for the impedance, and this is our suffix because we're doing electronics. We copy this down the entire column by double-clicking on this little square. All right, now we are ready to calculate the voltage gain. Now, we recall our voltage divider formula. V out over Vin is equal to the output impedance Z out divided by the sum of Z in plus Z out. And we remember that Z in is this column here, G, and Z out is this column, H. And so here we go with this formula. We're doing division because it is Z out divided by that sum of Z in plus Z out. And the numerator here is H6, which is Z out. The denominator is the sum of Z in plus Z out, so I use IMSUM. H6 is Z out, G6 is Z in, and that does all of that heavy lifting of that complex division. And now we copy this down the entire column by double-clicking over here. Now we have the voltage gain in complex form, but we want this value in magnitude. So we're going to create a column of values in J, which is just the magnitude or the length of this vector. To do that, we use the IMABS function. So it's equals IMABS, left parenthesis, this complex number. That will return the magnitude of the complex number. Again, we copy it down the entire column. We also want to have a grasp of the phase response of our circuit. This gets a bit hairier as we have to visit the complex plane. The phase is the angle between the real or x-axis and the vector. The angle is found with the following formula. Phase is equal to the inverse tangent or arctangent of y divided by x, which is equal to the arctangent or inverse tangent of the imaginary part of our complex number divided by the real part of our complex number. We use the imaginary and IMREAL functions to get at this. Furthermore, Excel thinks about angles in terms of radians, and we think of them in terms of degrees. So we use Excel's degrees function to convert the angle reported by Excel in radians into our familiar degrees. So we enter the following formula into K6. Degrees, this is what translates the radians to degrees. Arctan, this is the arctangent or inverse tangent. Now we're grabbing the imaginary portion of this complex number and we're dividing it by the real portion of that complex number. And we copy that down the entire column. Done. Now we have the phase response. Lastly, we'd like to have this voltage gain expressed in terms of dB. So we enter the following formula in L6 equals 20 times the log 10, this is the log to the base 10, left parenthesis, our value here from J6, right parenthesis, and we use the 20 times log because this is voltage gain as opposed to power gain. We copy that down the entire column. And now we have the voltage gain as expressed in dB. If you want to see this on a graph, then create your scatter graph using frequency as the x-axis in whichever entity, whether that's voltage gain or the voltage gain in dB or the phase, whatever you're interested in as the y values. But when you do, be sure to change the x-axis to show values in logarithmic sequence. To change this, click on the x-axis, then right-click, click on Format Axis from the drop-down menu, choose this icon over here in Format Axis, Axis Options, go down here, find the logarithmic scale, and just make sure that this is clicked. Without that clicked, this is what your graph is going to look like. With it clicked, this is what your graph looks like. Wow! That was way easier than slogging through the pencil and paper exercise. If you found this video helpful, please click on the like and subscribe to this channel. Don't forget to subscribe. Thank you so much for watching. Until next time, Toodle-Oots.